Welcome back. We are up to chapter 20 in our trek through the universe. The background that I have here is actually a supernova remnant. As we've talked about in a couple of different ways, the universe is the ultimate recycling plant. And what's happening here is that a massive star exploded and returned lots of stuff back out into the area around it, and thus it becomes a nebula again. So nebula is, again, a Latin word for cloud. And what we see here are clouds of dust and debris and particles and elements and molecules and residual energies and other things from something that was huge. And we'll talk about just how huge in a couple of lectures from now when we talk about the deaths of stars. But when we're talking about the stuff between the stars, a lot of the stuff that's out there now includes stuff exactly like this. And this will, in fact, turn into other stars and planets and people. The stuff in my body, the stuff in your body was manufactured in explosions just like this one. So in many ways, you are star stuff. And that's sort of a kind of poetic way of looking at it along the way. The more cynical way of looking at it is we're all nuclear waste products, which is true because all of this stuff out there is nuclear waste. It's not plutonium, it's not uranium, it's not that kind of nuclear waste. It's fusion reaction kinds of things and those kinds of binding together to make things. Anything that's higher essentially than hydrogen, helium, maybe just a little bit of lithium, but by the time we get up to carbon and oxygen and nitrogen and all of the other higher elements that are part of us, the calcium in our bones, the iron in our blood, all of those different kinds of things come from this kind of stuff that's out there, either the stars themselves or the explosions that end their lives. But we're going to take a look here at some of the different parts of what's spinning around out there. So we'll take a brief tour of what's often called the interstellar medium. And I'm going to see if I can share my screen. There we go. Chapter 20, Between the Stars, Gas and Dust. So let's play from the start here so we can see what's happening along the way. This one also is a cloud, as you can clearly see on the right-hand side over here. What's not quite as evident is there is a collapsing cloud all around these stars that are forming. This is a cluster of stars that are forming from the nebula, and it's really formed here. So this was a denser area of gas and dust that collapsed and is now, in fact, with the stars turning on, blowing the rest of the cloud away. And we'll see different elements of this kind of process as we take a look at different parts along the way. There are different types of interstellar matter. There's actually dust. In fact, a single-digit percentage of the dust particles that you dust at home have actually floated down from space through our atmosphere. There is also gas, there's also energy, there are all different kinds of things that we'll be seeing. And when we look at a picture such as this, one of the things we can see sort of down in the lower left is a big red star, Antares. If you're a Star Trek fan, you may have heard that star referenced a couple of different times as a place that they will sometimes travel to. We can see their blue areas, we can see their red areas. This gives us an indication of higher energy and lower energy. What we see is we have hot stars in the midst of the gas and dust that's there. So that's going to heat up some of the particles that are going on in that. We see this sort of blue cloud here being energized by a very hot star that's up here. We have sort of cooler gases that are happening down here. As long as we have stars energizing the nebula particles, they will not cool enough to collapse into yet more stars. They have to sort of get off on their own to cool down before that happens along the way. But we often refer to all of this stuff as interstellar media or the interstellar medium if we're sort of talking about it as all one big collective. If we're talking about it in constituent parts, we might use the plural media. We sometimes think about media as like newspapers and magazines and television shows and stuff like that. Along the way, media is actually a plural term. Medium is the singular term. But if we're talking about it all collectively, we're talking about it, the ISM, the ISM, the interstellar medium, and it's gas and dust that varies in terms of what it's made of. It varies about the temperature, and it varies upon the density. Sometimes it is more dense, sometimes it's less dense, sometimes it's almost a perfect vacuum. But when we're talking about it in general, it is a lot less dense than the air you're breathing now. So if you think about an empty balloon, that empty balloon still has more particles inside the balloon than our typical areas of interstellar medium. So it's really spread out. It is also in a constant state of motion. As you can sort of see from my backdrop here, there are all sorts of spindly waves and ebbs and flows and things that make it look like it's in motion. This is the result of the supernova blast, as well as different kinds of interactions, both gravitationally and energetically. Here we see a more sedate shockwave blast, supernova blast that is sort of coming out of a sort of central thing here. Obviously, whatever was in the center here has cooled off enough that it's not showing up in this photo, but we see the remnant. And this is going to be 3 dimensions. This isn't 2 dimensions. This is sort of going out like a bubble. And that's what will happen. Of course, these will happen in different ways. So sometimes we'll have bubbles hitting upon bubbles, or we'll have bubbles that are bumping up against other stars, or the areas that have been sort of jostled around by other stars. We have different clouds, but we have different kinds of components in it. So we'll talk about all of those different kinds of things that are here. It's worth paying attention to these things in your reading. If you go ahead and look at the midterm exam, I think that'll probably open like this, later this week or early next week. One of the questions is talk about interstellar media and the different types of things that are here. So this chart will show you, sort of in a handy dandy form, the different kinds of things that are out there, and we'll be talking about those. One of the things to notice the temperatures here. We go, and this is in Kelvin, so we start at absolute 0. 10 Kelvin is going to be minus 260 or so degrees in Celsius, or minus 440, 430 degrees in Fahrenheit. So we're talking really, really cold here in molecular clouds. When we get up to this 10 to the second, that's 100. 100 Kelvin is still minus 173 degrees Celsius, so that's still really, really cold. Think Alaska on a cold day, or North Dakota on a really cold day. Actually, it gets, this is so much colder than that along the way. By the time we're getting up to H2 clouds, and by the time we're getting up into the warm interstellar medium, we're talking some real temperatures here of what we would consider to be hot rather than cold or almost frozen. And coronal gas, when we're looking at 10 to the 6th here, we're talking 1 million. So we're talking really, really hot. If you're 1 million Kelvin, if you're 1 million degrees Celsius, which is essentially what they are because they're only 273 degrees off of each other, that's really, really hot. By the time you convert it up to Fahrenheit, which is pushing us up closer to 2 million degrees, yeah, pretty hot. But one of the things to notice is the density here. And when we're talking about density, atoms per cubic centimeter, so sort of you have the cubic centimeter, how many are in there. These are almost vacuums. These are almost vacuums that we see here in terms of numbers of particles. So if we had a sort of a typical high school laboratory where you would make a vacuum, it might have actually more particles in the vacuum than some of these areas here, especially when we're talking about the H2 clouds or the warm interstellar medium along the way. But when we're looking at a nebula, and this is the Orion Nebula, so if you go out, especially in the winter time, to look for the Orion constellation, it's going to be the 3 stars in the middle. Go to the one that's on the left, sort of the lower left, put your hand up like this, and it'll be about halfway down your hand. That's where the Orion Nebula is going to be. It really doesn't matter what size your hand is, because somehow it sort of works. Your hand and arm relationship to each other, that tends to work along the way. Plus, close is good in this kind of astronomy. Close is good. You can see it with good binoculars or sort of a regular telescope. It'll just begin to form in your view there if you have some good viewing along the way. We see a lot of hydrogen in this. We talked a little bit about different lines that we get from the spectral analysis, the Balmer lines in hydrogen. We see quite a lot of that in here. But we also see other things happening, including this middle portion here. This is a nursery. This is a stellar nursery where stars are being born along the way. When we look at molecular clouds are not often just free floating atoms and electrons and protons. That means that they're cool enough that things have bound together. Inside of stars, things are too hot for that to happen, because not only would molecules be ripped apart under the heat, but also the electrons get stripped off the protons in the heat, whereas when you cool down, they will naturally coalesce together. And hydrogen doesn't like to live by itself. Helium doesn't tend to like to live by itself. They tend to glom together into molecules. So you'll see H2 and He2 and other kinds of molecules that are out there. A lot of atoms don't like to exist just off by themselves. You won't find a lot of oxygen atoms just by themselves. Oxygen likes to combine with other things, same as carbon. But these will be cool, these will be cold, but they'll also be denser in terms of the materials that are out there, in part because the molecules are heavier. The molecule, if you've got a molecule of H2O, it is denser just because it's got 2 H's and an O than 1 H over here, or even 2 H's over here along the way. So this is where, by the time things have cooled off, gravity can then take over and begin to pull things, whereas if they were more energized, if they had a higher temperature, they would still be flinging themselves apart from each other. So this is where stars begin to form, molecular clouds. And we can look at molecular clouds and we can get the different absorption lines that we see from them, especially if we have a good test star to be behind them that's sort of sending its light behind. But we can also get different kinds of readings off of the clouds themselves, especially in infrared. And we can get the different absorption lines that we see here. And we can tell what would be coming off of a star without the cloud, and then we can see what's coming from it combined. And that way, one of the things we can do is take away the stellar lines. What's left over is our cloud. When we're talking about H1 clouds, we're talking about low temperature hydrogen gas. So quite frequently in these, we're going to have atomic hydrogen. There is enough energy to sort of keep things going as sort of separate atoms that are there. These will often be found in the galaxy's disk and the spiral arms. So when we're looking at this, one of the things that we see, there's a particular thing called the 21 centimeter line. And the 21 centimeter line is a particular reading that we take. I'm not going to sort of bore you with all the technical details of it, but it's one of the readings that we take that's pretty standard when we're dealing with a hydrogen. And it's a good way to gauge what hydrogen does and where hydrogen is. And one of the things we can see when we're looking at in this particular way is that we have a very wide range of densities. Sometimes it's rather low density, scattered. Sometimes it's rather high density and sort of coalescing along the way. One of the things that we see when we're talking about that 21 centimeter line is when we have electrons going around protons. Sometimes they will be spinning in the same direction, sometimes they'll be spinning in the opposite direction. When it flips, depending upon whether it's absorbing or emitting energy, what we get as a reading comes across in a wavelength of 21 centimeters. And that's true for hydrogen everywhere. So it makes a good marker along the way. What happens, of course, is that when we have these photons emitted or absorbed, we can watch this happening. We can do this actually here in our own experiments. We don't have to just rely on it happening out there. So we know what it's like, we know how it works along the way. But our lower energy state has them in opposite directions. Our higher energy state has them going in the same directions. So we can tell whether or not it's emitting or absorbing, whether it's a higher or lower energy. Some of the ways in which this was really first pioneered and developed as a method was by Ewan and Purcell in the mid-20th century, and you can sort of see the kind of equipment that they have here. They won the Nobel Prize for physics. There's not a separate one for astronomy. So there's also not a separate one for mathematics. I might tell you the story as to why, the purported story as to why, sometime in the future. It's rather interesting. I went to visit the Nobel Prize, the hall in Stockholm where they award the Nobel Prize, and it is a sort of interesting story. So I'll think about telling you the Nobel Prize story history maybe a little bit later in the term along the way. But they won the Nobel Prize a few years after this. Sometimes it takes 20 or 30 years after a discovery or a development of a technique before you win. So this was recognized early on as being very important and fundamental to the way we look at things. And here's our Vela Supernova, which is the thing that I have behind us here. One of the things that you might notice is that this part that is behind me is this middle section here. And it's this middle section here sort of turned on its side. So again, up is not always north in photos that we're looking at here, but notice the range of clouds, notice the different types of clouds that we have here along the way. What we're seeing is we have lots of these wave front lines. We call those filaments. And one of the things that happens is as the shock waves go, it'll push the material together, and sometimes that will bond together molecularly. Sometimes it will bond together gravitationally along the way. So what we see is the shock waves here are colliding with other interstellar medium collections that were already out there, and it's heating all of this material up as well as that happens. So when we're looking at H2 regions, one of the things that we're looking at here is we're looking at areas where we have the hydrogen, which has been sort of stripped off of some of its material along the way. So quite frequently what we will see when we're dealing with this is a higher energy area. Then when we have our warm interstellar medium, this is stuff that is warmed by all the different kinds of material or radiation that's out there. So it can be warmed by starlight, it can be warmed by the shock wave fronts, it can be warmed by any number of stuff that's out there. And it has temperatures that are similar to our H2 regions that are out there. So a little higher temperature along the way from the H1 to the H2, but it tends to have less material along the way. And then we have coronal gas. Coronal gas is quite frequently what we call these sort of bubbles of material that are coming off of supernova explosions. We have coronal gas that's around our sun. It stays around our sun. It's part of the atmosphere of our sun. But if our sun were to explode and we'll talk about why a supernova explosion isn't in our sun's future history when we talk more about how that happens. But for really big stars, they have a really big blast. And what will happen is we'll have a blast that sort of bulges out. And if it's nearer the top or the bottom of the disk in our galaxy, it will also create this sort of fountain effect. This is usually very, very hot stuff. And the corona around our sun is very, very hot stuff. It's 1,000,000 degrees or more in temperature along the way. So this stuff can go in either direction. You notice it's not going in both directions because usually it's near one opening or another. So if it's right in the middle, it's just going to create a sort of a bubble, sort of like this one here or these two that are over here. But if it's right near the top or right near the bottom, there's nothing in the top or the bottom to shield the big fountain effect, but it's not going to go down below as well because there it's hitting stuff along the way. So what we see is that this then will mostly fall back into the plane of the galaxy and combine with the other forms of interstellar medium that are out there along the way. So these are very high temperature, and what we get is a kind of almost sort of, as it says on our thing here, Swiss cheese network kind of thing. So we have intense area and nothing, and intense area and nothing, and intense area and nothing along the way based on this. There are supernova explosions in our galaxy pretty much every 30 to 100 years. So this is happening, and when you're around for billions and billions of years, that's not very long in between the different supernova explosions. So this is happening again and again and again and again and again and again and again. We're sort of overdue for a supernova explosion. There were two of them about 400 years ago or so, within a generation of each other. There was Tycho's, and then there was Kepler's supernova explosions. We really haven't had one that features in our night sky that we can see with the naked eye since then. So we're a couple of 100 years overdue, and Betelgeuse might be it. If Betelgeuse happens, we're going to have one of these fountain effects that will blow up. It'll take thousands of years for this fountain to sort of reach its maximum intensity above or below the disk of the galaxy. So we have a lot of different clouds that are out there. They're often together. So we will have H1 clouds, H2 clouds, warm ISM clouds, WISM clouds, molecular clouds that will sort of be overlapping in each other in the way that we look at things. But we have to remember we're looking at things pretty much two-dimensionally that are in fact three-dimensionally along the way. So one of the things that we will see is that they often reach an equilibrium point where you'll have these bubbles within the clouds that will be primarily one thing or the other. When we're looking at these clouds, we can often tell what's happening inside of them and what they're made up of by the light that gets through them, especially if there's something behind them. Because radio waves don't tend to be affected by larger grains. Infrared is also less affected, but it is affected by that. Visual light will often be obscured. Notice what's happening here. The longer the wave, the more likely it is to get through. The shorter the wave, the more likely it is to be blocked. And when we go beyond the visible, in shorter and shorter and shorter, we're talking about gamma rays and X-rays and other things. Those things tend to be blocked as well. But it will sometimes be the case that they'll be blocked in certain wavelengths and not others. And that will also give us a clue as to what the clouds are made of along the way. So when we're looking at the different kinds of effects that we have some areas that we would call absorption, and we have some areas that we would call emission clouds. So absorption and emission clouds operate differently, and they actually look different in what we're doing. And then, of course, sometimes we have some really interesting kinds of stuff that's out there. fullerene, which is C60 carbon, carbon atoms. Carbon atoms never, ever, 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 ever like to be off on their own. They are the most promiscuous atoms in the set of elements that we have, 92 naturally occurring elements, and carbon is the one that will go home with anyone. That's how my organic chemistry professor once described it. It is the atom that will go home. It is the element that will go home with anyone, doesn't matter who. And as a result, that's one of the reasons why organic chemistry in particular is as dynamic as it is, and why life is based on carbon, and why there are so many different varieties and different kinds of details that are around that. But what we see is carbon is in a lot of these clouds, and carbon will combine given the right conditions that we have. Again, not too high of a temperature, not too many things pushing things apart, but we even get these large complex things like the buckyballs. There are some nebulae out there that have the chemical composition of alcohol, because alcohol in its various forms will have carbon and will have hydrogen and will be in different kinds of structures that are out there. So there are entire beer nebulae that are out there. That's not a reason to support the space agency, the space program, to get out there and go collecting stuff. You never know what microbreweries are happening out there in space. And I'm actually not making that up. That is not a joke. That would not be a bad final project, to look for the beer nebulae and talk about the chemical composition and how they're formed together, because we're talking about the different kinds of carbon stuff that's out there. Well, these clouds eventually will coalesce into stuff that we see as stars and planets and other things that are going around along the way. Molecules are gravitationally attracted to each other, just in the same way everything else that has mass is attracted to each other in the universe. But gravity is a very weak force. It's almost an ironic kind of force, because ultimately gravity wins in the universe. But it's like, if I'm looking at something here, it's like I'm picking this up. I'm defying gravity here, because gravity, I'm working against gravity by picking anything up. I'm working against gravity by just simply standing up or sitting up. I'm not letting gravity win. But if you cool things off, and the sort of energetic motions inside of the atoms and molecules slow down enough, then gravity begins to win and pulls things together. And you add to that the chemical attraction, the chemical bonding, where different elements, different atoms will stick together. Then pulling those chemical structures apart requires more energy, and of course you're in a cooling phase, so typically that's not going to happen. So what we often have is various kinds of reactions that happen. Now sometimes the chemical reactions will produce some energy, and it'll re-release kinds of things that are out there, but in general what happens is these little grains grow over time. And even as they don't grow themselves, if they don't grow themselves, and most of them will over time, they're beginning to produce heavier and heavier molecules that are out there. And that combined with the coolness means that we have more and more and more things that are heavier and heavier and heavier attracted to each other. Two H molecules, if they were the only things around, would be attracted to each other. But two H2 molecules are going to have twice the mass as the ones before, so they're going to be even more attracted. H2Os have a lot more mass than the H2s or the H's, so they're going to be a lot more attracted, and that's what ultimately happens. When we have giant molecular clouds, like we have in the Orion Nebula here, we can have as much as 10 million weights of the sun, masses of the sun, in these clouds. So we could make up to 10 million stars the size of our sun from this. And this is light years and light years and light years. Remember this number here. parsecs. Parsecs is 3.26 light years across. So when we're talking 10 to hundreds of parsecs, we're talking like 30 light years to hundreds, if not thousands, of light years across. It can be one huge thing along the way. When we think about our own solar system's size, it's not even close to 1 light year, so forget about it. Our solar system is more on the order of about 1/100th of a light year. That's if you give a generous reading to how large the Kuiper belt is, which is the area where comets and Pluto and other dwarf planet kinds of things will be. Here's a good example of what we might call an absorption cloud. These are sometimes called Bok globules if they have certain characteristics. Bok is actually Bok and Bok. It was a husband and wife team for whom this is named. There's a book that I read when I was studying astronomy by the Boks, and they are the ones who came up with the classifications for these. They're usually small. So whereas the Orion Nebula over here has 10 million sizes mass of the sun, here we have only just a couple along the way. So these are cool, typically cooler. These will often coalesce into just 1 or 2 stars eventually along the way. Sometimes we have them obscuring other things, so they look like they're like a hole in space, this Barnard object that we have here. So one of the things we can see is it sort of looks like a heart there, a little misshapen as a heart. But scientists can be dorky sometimes, so there was one astronomer who used this as, you rotate it, you can use it as a Valentine along the way. But one of the interesting things about these is that you can, if you look at it through infrared or you look at it through radio waves, see through it. So even though it's blocking the visual light here, that doesn't mean it's completely empty. And that was one of the things in the 20th century we began to understand, is that sometimes we can see through other things along the way. Here's Barnard himself with one of the early large telescopes that we had in the late 1800s through to the middle 1900s. There was a sort of a craze to get bigger and bigger and bigger observatories. We're still doing that now in a sort of a renewed phase of that kind of operation. But one of the things that we know from Barnard himself is that you can see a lot of things that are out there that are not always explainable just in sort of Roy G. Biv light. And that becomes an important understanding as we begin to look at especially things that are outside of our galaxy, because as we look at things that go beyond, we come up to the limits of what we can see with our Roy G. Biv eyes. Now, when we are able to combine those different kinds of ways of looking at things, like here, when we're looking at the Horsehead Nebula, this is also part of Orion. This is an absorption portion of the nebula, so it's sort of a big gas cloud that's sort of sticking out there, has sort of dense dust and molecular structures to it. But when we look at it in our infrared region over here above the letter B, we can almost see right through it. It becomes rather transparent. So it's almost like we're looking at an X-ray, but we're not looking at X-rays here. We're looking at infrared. And remember, infrared, if we sort of go back to a couple more of these, notice the visible light is being blocked, but the infrared is going through. So when we're looking at it in our infrared, we've got some indications that things are going through. Notice how bright this area is here off to the left. It's got a big dark patch here, but we see the brightness in the infrared. And when we're looking at this central area that's here, we can see in Roy G. Biv, we can see a lot more with a lot more structure attached to it when we're looking at it in the infrared. And when we're looking at these kinds of things, we have different ways of analyzing. And sometimes what astronomers will do is they will blend together the images. And what we'll have a couple of times through our semester are blended images. When we're looking at infrared just in general, what's out there, the Spitzer, I think I've mentioned the Spitzer before. I may have even shown you the book, More Things in the Heavens, which is a sort of book commemorating the Spitzer Space Telescope, major observatory of the NASA program, just went offline earlier this year, just a couple of months ago, in fact. This is a look at our Milky Way galaxy. And what we're doing is we're sort of looking all the way around us. So what you would need to do is take this on a strip and put it around so you can look all the way around you along the way. And this is looking at our galaxy edge on. We're inside, so we're looking at it from the inside edge on. And we're looking at it in infrared. We're looking for heat signatures here. So what we're seeing are tiny dust grains that give us a blue image, and some that are a little bit cooler in green, and some that are a little bit cooler in red that are there. And these are sort of artificial because we can't see infrared. So an actual picture of infrared would just like, nope, sorry, can't see anything. So it's sort of like if you're in music and you're playing a tune and someone says, I can't sing that high. It's like, okay, you're playing for soprano and I haven't been a soprano since I was 10. So you've got to bring it down. That's what's happening here. They're transposing the light into something that we can see. The 3.6 microns are going to be higher energy, the 8 is going to be mid-range, and the 24 is going to be lower energy because that's the way light works for what we see. That's true everywhere. That's true in X-rays. You're going to have some higher energy X-rays and some lower energy X-rays. You're going to have some higher energy infrared and lower energy infrared. And you can, when you're transposing that up or down, you can see this kind of stuff here. But one of the things that we're also seeing is that the denser areas tend to be cold. So we have some dark clouds even with the heat signature stuff here. And we have almost a little bit of sort of an anomaly here because we're getting heating increases in the red. And that's where we're sort of seeing the reddish colors that are there. Then we have this. And this is the Pleiades. And this is one of my favorite things to go out and look at with binoculars or with a low power telescope. You can sort of go to Walmart or go to Target and buy the telescope off the shelf, and it's about $70, and it's really not that great, except when you're looking at the occasional planet, the moon, or this. This is the one stellar thing that is really okay to look at with low power telescopes or with binoculars because you're going to actually see something. You can actually see the gas and dust that's around here, the wispiness here, with the naked eye without any help. If you've got a really nice dark sky, you're going to actually see with your eye, with the unaided eye, some of the wispiness that's around here. And what's happening, of course, is these stars are formed out of the gas and dust, but these are huge big stars, so they are huge power sources, and they're energizing to a huge extent. I'm using huge a lot, I know, the gases that are here, which is why they've got the blue. This is a very high energy area that's here. But one of the things we can also see is when we're looking at this, it's sometimes been called the Seven Sisters, and we sometimes wonder exactly which seven the ancient astronomers were seeing, because these two often blend together with the naked eye. These certainly all blend together, and we're sort of counting if these two are together. We've got 1, 2, 3, 4, 5, 6. Was this the seventh? Was this the seventh? Could it have been brighter once upon a time? Were these two blending together to the naked eye and making it look like it was the seventh? So even when we look at it with just slightly better magnification, we can see that it breaks into a lot more than 7 stars. When you look at it with binoculars, you're going to usually see maybe as many as a couple of dozen stars. When you look at it with even a mid-range telescope that you can still buy like on Amazon.com, you don't have to go Hubble on it, you're going to see hundreds of stars that are here. This is about 400 light years away from the sun. So in terms of galactic sort of addresses, this is actually pretty close. Remember, the center of the galaxy is 28 to 30,000 light years away. The other side of the galaxy is as much as 100,000 light years away by the time we're getting past the edge and where the other arm is going to end on the other side. So 400 light years away, that's not in our neighborhood, but not in our sort of village where we live, but it might be in the same county where we live. Certainly within the same state where we live. If we think about the galaxy as being neighborhoods and cities and counties and states and countries, this one is clearly in the same country, probably in the same state, probably maybe even in the same county as we are in terms of its distance. And here we have that same Barnard image that I showed you before. Oops, there. Notice how dark it is. And then when we're looking at it in infrared, ta-da, there we go. We can see through it. And one of the things we can see is that it in fact is not a hole in space, that there's stuff behind it along the way. So this becomes an important thing. And one of the things that it highlights for us is this thing called interstellar extinction. When we're using the term extinction here, we're not meaning like going extinct like the dinosaurs. What we're meaning here is like extinguishing a candle. As light goes through and hits something like this, it gets extinguished. And as light goes through in most wave ranges, even including infrared, even including radio and other things, there are things out there that will interfere. There are some things that are less prone to interference. There are some things that are more prone to interference. But this interstellar extinction, this interstellar medium extinction is a real issue along the way. Another thing that happens, not just in terms of the extinction, is scattering. As light bounces off of different particles there, it can bounce off into different directions along the way. And we see that here on Earth. If I shine a light on something, the light scatters off of it. So I sort of take my flashlight and the light scatters in that direction, and the light scatters in that direction, and the light scatters in that direction. So that happens out in space as well. When we're looking at the dust grains, and we've actually had some sample return missions. The JAXA, the Japanese Space Agency, has had sample return missions where they've sent something through a comet tail and brought back some grains from that. So that's not perhaps typical interstellar grain, but it's a typical thing that we might have out in our solar system. It's going to be not too dissimilar to what's happening out there in space. One of the things we can see is that we might have some water particles, some water molecules there. We might have some carbon-based things that are out there, like methane or ethane or other kinds of, even as I mentioned before, alcohol kinds of things. We might have ammonia that's out here. Notice one of the things that's sort of everywhere you look, H, hydrogen is everywhere, but we've got the different higher elements that are out there along the way. So we might have some rocky material like something like silicon, something like iron, something like zinc, something heavier that's there. But these are going to be very, very tiny. These are going to be even tinier than the stuff that you dust up from your home. We've been able to do some work on this kind of stuff that's out in the universe. As long as we've been able to take any kind of detector up a little bit above the atmosphere, the density of the atmosphere down here on the ground. So one of the early pioneers is a guy named Victor Hess, and notice here he's getting into a hot air balloon. and he goes up several miles. If you think of about a kilometer as being 0.6 of a mile here, so we're sort of not quite getting into the 4 or 5 mile range when we're at 5.3 kilometers. So in fact, he would have been higher into the sky had he climbed Mount Everest than this. That's here, but still, this was a very interesting first thought experiment that became an actual experiment, going up above the density of the atmosphere. The atmosphere here is denser than it is here, and the atmosphere here is denser than it is here. The higher you get, the less atmosphere there is. You go to Denver. What's the stadium name in Denver? Mile High Stadium. Why is it called Mile High? Well, that's because it's a mile above, over 5,000 feet above sea level. The temperature or the atmospheric density that's there is less than the atmospheric density, say, in Houston or New Orleans or Chicago or other places that are sort of on the coast and thus they're at sea level along the way. If you drive up into the mountains of Colorado, your car sometimes might have engine knock or other kinds of issues because temperatures, the temperature at which water boils, the temperature at which gasoline reacts in your engine differs based on atmospheric pressure. And by the time you get up to the top of Mount Everest or K2 or Mount Kilimanjaro or other major peaks, you're so far up there, it's hard to breathe. It becomes a struggle. So you're having less atmosphere block things. Cosmic rays typically don't make it through the atmosphere. They don't. X-rays also don't typically make it through the atmosphere. Gamma rays don't. But if you go up high enough, they're still there. It's just when the atmosphere becomes thicker and thicker and thicker down here that it blocks a lot of that along the way. So this was an innovative kind of thing that's out there. When we're looking at where all of this matter is, all of this material, this is an interesting large-scale simulation of our galaxy. One of the things that I would throw into a little bit of a question with this simulation is the center should be a little bit more elongated because we're in a barred spiral that's here, although it may be that the interstellar medium, interstellar matter that we have in our galaxy doesn't quite bar in the middle the way other things do. And that is entirely possible along the way. But we have lots of shapes, lots of sizes, lots of different components to it. Everything has a motion to it, unless it's at absolute zero, and we can forget about that happening. And because of that, they're also going to have electric charges. The protons have positive, electrons have negative, so combine things together, we're going to have various magnetic and electronic things happening along the way. So as we look at experiments in our own laboratories of how turbulence and fluids operate, we can actually make some observation and analysis decisions on what we're seeing in space, because we can't go up there and do actual kinds of experimentations that are there. When we look at the sky in X-rays, remember we just saw our galaxy across the middle there in infrared. When we're looking at X-rays, again, what we're seeing here is we're taking the X-rays and shifting them down, because X-rays are much higher in terms of energy and a shorter wavelength than Roy G. Biv. What we've done is we've sort of shifted it down. We have the plane of the galaxy that's right in the middle there. We have some interesting spots that we're seeing here, and we'll talk about what some of those are along the way. We have this sort of big green area that's here, sort of in the middle. And one of the things that has happened in fairly recent astronomy is the understanding that there are these sort of huge X-ray bubbles above and below the disk of our galaxy. And we here in the sun's vicinity here, we live in an area called the local fluff. We are in fact inside of a very low density cloud there. So as we're looking out, we don't tend to see all the wispy filaments and stuff that we would see around a supernova area, but we do in fact have gas and dust that's part of our local neighborhood. Notice a couple of other stars you might recognize the name, Sirius, Alpha Centauri. They're part of our local neighborhood. They are actually part of this huge cloud that is part of the local fluff. The galactic center is going to be in this direction. Our sun's motion relative to that is up like this. But as we'll see when we talk about galactic motions, our sun actually goes like this around the galaxy. So it's not that we're heading away from the galactic center, we're sort of going around it, but we're going around it sometimes up and down in different ways. Our solar system is formed from a nebula, but most likely this is not the nebula that is what formed us. This is a different one that we've sort of come through and we're going through. And as we come through and go through it, we're obviously disrupting the cloud. The heat from our sun, the motion of our sun is disrupting all of this. And we are expected to be in this cloud for some time. As you see, it says down here, another 10 to 20,000 years. So that's a while, as it says. So it may be a while before we can actually look out into the sky and see something like what I've got behind me here, just in the regular nighttime sky. Might not be so good for us if we did look out and see this kind of stuff, because this stuff is really interesting. And I may have mentioned before, in astronomy, the word interesting usually means radiation. You don't really want your planet to be somewhere really, really close by all of this stuff. So being out in the local fluff, I'm happy to be fluffy. We are in an area that is reasonably safe, reasonably insulated, and reasonably far away from anything that might be literally earth-shattering. So I look forward to seeing you again in chapter 21. So stay tuned for that.